Hello, here we will use methods of orthogonal algebra, linear algebra to produce what are called orthogonal polynomials. They appear in various kinds and depends on which scalar product we are using. So we will be looking at the space of polynomials, say starting writing them through the standard monomial basis. And they can be thought of as, say, smooth functions with first continuous derivative on an interval like that, on a closed interval between -1 and 1. And with this way of seeing them, we could we could look at the scalar product on the vector space of all these functions, which is given by this integral of the product. And that was checked before, that this is a scalar product. And now we could use orthogonal algebra to, say, produce an orthogonal basis in the subspace. So instead of monomial basis, which is not going to be orthogonal for this scalar product, we could, perhaps by applying a version of Gram-Schmidt process, we could produce a sequence of polynomials which will be orthogonal with respect to the scalar product, meaning that if we take two different polynomials from the list, the answer will be 0. So in this setup, for this scalar product, the resulting polynomials which we get using Gram-Schmidt process are called Legendre polynomials, up to a coefficient. And the Gram-Schmidt process naturally gives us a sequence of polynomials which will have the same degrees as their sort of original versions. Because what we will be doing is we'll be adjusting next polynomial in the list by subtracting the projection onto the previously computed orthogonal polynomials. Previously computed polynomials by induction will have a lower degree, and so the resulting polynomial will have the degree the same as the thing which we are adjusting, which we are projecting. So let's just start with Gram-Schmidt process. The first step is just the polynomial which we're looking at, namely this constant polynomial 1, the first vector in the original basis. Nothing to do. To compute the next one, we have to take the next vector and modify it by subtracting the first already, so the 0th vector in the basis, with a coefficient so that the resulting difference will be orthogonal to the first vector. And the recipe is just compute these two numbers. They are given as scalar products, this thing in our case, and then the ratio will be the right coefficient. So we need to compute these two numbers. We need to compute the scalar product of the constant polynomial with itself. And that is the easiest thing, because we're just integrating one constant 1 function between -1 and 1. The answer is 2, right? Just geometrically what we're looking at is the area under the graph of the constant function between -1 and 1. Clearly the area is 2. Or we could find the prime function, which will be x, and then take the values at 1 and -1, take the difference, we'll still have 2. So that is going to be the denominator. And the numerator is going to be the scalar product of x and the constant 1. And that is, again, everything is computed by integrals and not just integral of x. And this time, the answer is going to be, if we draw the graph, the answer for the signed area, that's what the integral computes, is going to be 0, because we'll have the same contribution in minus and plus areas for this graph. Or computing the prime function, which is x squared over 2, and computing the difference of values, we will have 1/2 minus 1/2, so it will be 0. And that is a general phenomenon, either looking geometrically or algebraically. If we integrate something which is of odd degree, a kind of homogeneous odd degree polynomial, basically it's an odd power of x. If we integrate it between a negative and positive value, the same value, the answer is going to be 0, just because the graph is going to be anti-symmetric with respect to the origin. There will be as much negative area as a positive area, doesn't matter what it is. So the answer is going to be 0. Let me just write down this general fact. So if we have an odd degree polynomial integrated like that, the answer is going to be 0 always. And that was what happened here in particular, and the result is going to be just x. So P1 is going to be the same vector as we have in the list. They are orthogonal. Let's proceed with P2. So let's just push this Gram-Schmidt process as far as the sheet of paper is allowing us. So the recipe is to take the next vector in the list and adjust it by subtracting the previously two computed vectors with some coefficients. So what will happen in here, we will have to compute scalar products of x squared, the vector which we are adjusting, and the denominators are going to be scalar squares of the vectors we are projecting onto. And in this case, we have P1, which is x, and then we have x squared. So this scalar product, x squared with P1, is going to be the integral of x cubed. We're multiplying x squared by x. And by this rule, going to be 0. So that is not going to, this vector is not going to appear. Its contribution is 0. And the only interesting coefficient is in here. So let's see what it is. That is again the integral of just x squared. So this time the power is even, and the integral is going to be interesting. The prime function is, for example, x cubed over 3. Then we have to evaluate it at 1 and -1, take the difference of values. The values will be the same, and absolute value will be 1/3, but with negative sign, but the negative sign disappears because of the difference taken, and we just have 2 over 3 as the answer. And that is the coefficient in the numerator. The denominator is the same scalar product which we computed before, and P0 is just 1. And so what we are looking at is x cubed minus 1/3. So let's just make the answer pretty and use this normalization, so rather non-standard normalization, but normalization such that all coefficients for all powers of x are integers, not rational numbers, as they allowed to be. And that would require just scaling it up by 3. So P2 will be 3x cubed minus 1. So continuing with the next one, that perhaps will be the last, P3. or maybe not the last, P3 is the result of projecting x cubed on the previously computed vectors. And by the same principle, we could see that P naught will have a contribution with coefficient 0 because the scalar product of x cubed and P naught, this again will be given by the integral of that shape. So the only interesting, and the same for P2, the only interesting will be coming from P1. This is a special feature of integration over the centrally symmetric interval centered at the origin. That is why odd functions, odd powers of x, for example, will integrate to 0. Even functions, however, will not, so we'll have to compute two numbers, two scalar products, P1 with itself. That will be, P1 is just x, that will be the integral of x squared. But we already computed it, it's 2 over 3. So that's what will appear in the denominator, the third of x. The numerator will have to compute again, or not again, but just compute. That will be the integral of x to the 4 prime function, this time is x to the 5 over 5 at 1 and -1. So the value of the evaluation is 1/5, so we'll have 2/5 as a result. And then simplifying it as much as we can, we'll have x cubed minus 3/5 x. And again, doing the same normalization, calling it a preliminary answer and making the final clear in the denominator, we'll have 5x, this is x squared, 5x cubed minus 3x. And maybe just the last computation for the next x to the 4. So this time, by the same principle, ignoring the odd, since it's even power, its projection will be non-zero only for the even orthogonal polynomials, and there are two such, P0 and P2. And we can ignore the other two, P1 and P3, because coefficients which they appear with will be 0. This we already know the answer for. It will be 2 rather than 1. It is computed here. X to the 4 and then 1 we computed before. This integral is 2 over 5. And for P2, which is 3x squared minus 1, we will have to do it separately. So P2 with itself, first this scalar squared, -1, 1, 3x squared minus 1 all squared, the integral of. And probably the easiest is just to compute the square, open it up, and then write it as a polynomial, as a sum of powers, and then write the prime function for it and evaluate it. So when we compute the square, we'll have 9x to the 4, and then -6x squared plus 1. Writing the prime function for this, we will have to just find the prime function which are the summons. And then the first summon will be in 9 over 5x to the 5. The second will be -6 of 3x cubed. The last will be just x. The values at 1 and -1. And this is just 2. So when we compute the values at 1 and -1, it's enough to compute the value at one of the points and then double the result. So at 1, I will have 9/5 from the first term. The second term is just -2, and the last is +1. So what we have is 9/5 without 1. 1 is just 5/5, so we'll have 4/5, but twice gives us 8/5. That is the numerator here, denominator rather. Finally, computing the numerator will be integrating x to the 4 multiplied with 3x squared minus 1. Just multiplying, just opening the brackets, we'll have 3x to the 6th power minus x to the 4 dx. And the prime function in this case will be 3/7x to the 7 without x to the 5th power over 5 values at 1, -1, the difference of. Again, the same shortcut, just computing twice the value at 1. 3/7 without 1/5. And the common denominator is 35. I will have 15 without 7. That is going to be 8, and then we're taking it twice, so the result is going to be 16. So 16/35 is the coefficient. Final arithmetic. Let's just simplify it quickly here. So we'll have 1/5 coming from here, so that is nothing but 1/5. Maybe writing one more step. So x to the 4 without 1/5. And then here we can do the cancellation, leaving us with 7 and 8. So it is 2/7 as a coefficient for 3x squared minus 1. And finally the arithmetic, so x to the 4th. X squared appears with coefficient 6/7. And then the free term is a combination of -1/5 and +2/7. Doing it separately. 2/7 without 1/5. What we'll have is 35 as a common denominator, and then 10 without 7. It's just 3. So that will be, with positive sign, that will be our 3 term. And again, calling it a preliminary answer, the final integer polynomial will be with coefficient 35 for x to the 4. X squared will have coefficient 30. And the free term will be just 3. So that is as far as we can go. We run out of space, but the process can be continued forever. And of course, this computation is straightforward. Computing integrals is not much of a fun. Repeating it just without any tricks. But there is easy trick, which results in a recursive formula. So if you look it up, the Legendre polynomials satisfy in nice recursion. Just a simple warning that our normalization is different to other sources, so the recursion will have to be modified for what we have here, but it is still possible. So See you later.